and allow everyone to join. I can see a few familiar faces here, and lovely to see a few lots of people joining. So thanks everyone. Good afternoon. So welcome to the University of Sydney Architecture, Design and Planning's Session 2 ADP Speaker Series. My name is Daniel Ryan. I'm the Programme Director of Architectural Science at the University of Sydney. And we're really excited to be producing our online series this afternoon, which PC Thomas will be presenting. And PC is going to talk about why it's so difficult to reliably model thermal performance of a house. And we had a good chat about that yesterday, and really looking forward to how you'll go in depth about this. So many of you will know PC. Some of you, if you've done our program in sustainable design, will have been taught by him. Many of you in practice will have worked with PC or certainly attended others of his presentations. And in Australia, PC is probably one of the gurus of environmental design, but one of the clearest teachers around, and we're really delighted to hear from him. He specializes in integrated building design using simulation tools to assist in the design and delivery of sustainable buildings, particularly in predicting the performance of the mechanical services. He's a master's in mechanical engineering, 30 years of consulting, research, and teaching experience in sustainable buildings, building energy simulation, energy auditing, energy efficiency in buildings, and solar energy. He understands the philosophy of all green building rating schemes in Australia that relate to non-residential buildings, namely the National Association of Neighbours, the mandatory commercial building disclosure scheme, Green Star, and Section J of the BCA. He's involved at some level with teaching, developing, or reviewing each of them. PC enjoys working in team environment to help design and retrofit buildings to deliver sustainable high-performance buildings, and is founding director of Team Catalyst with the motto driving sustainability through teamwork. And he's also an adjunct associate professor at the University of Sydney. So just a little bit about today. So at the end, if you have any questions, please use the Q&A box to ask your question. In the event that there are technical issues we can't overcome and we have to cancel, the recorded version of the presentation will be emailed in coming days. At the end of the lecture, we'll have Q&A session, which will run through our live chat box. We ask that you please stay on mute and turn off your camera throughout this lecture, only asking questions in the chat. And so when it comes to Q&A, I'll be asking you questions to our presenters. And finally, before I hand over to PC, I'd like to acknowledge and pay respects to the traditional owners on the land on which we meet. So I'm here, the Gadigal people of the Eora Nation, and it's on their ancestral lands that the University of Sydney is built. As we share knowledge, teaching, learning, and research practices within this university, may we pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. So without further ado, I'll hand over to yourself, PC.
Thanks, Daniel. I'll just double check that you can hear me.
I can hear you fine.
Perfect. All right. Thank you for the opportunity to provide this lecture to the University of Sydney. I've probably been teaching there now for well over 17 odd years. Alan Obrat and myself started a course on code compliance many years ago. Softwares have changed, courses have changed, and we're still around. So that's nice to see. Also, I think I should say that modeling houses or residential buildings and apartments is rather new to our company. We've made a mark with commercial buildings, and particularly with helping commercial buildings reach energy efficiency and comfort targets. So residential is a bit new, but however, we've been involved in the new GBCA Future Home Standard, and we're working with the ABCB on the proposed changes to the National Construction Code for 2022, sorry. So we've learned a lot along the way which I wanted to share. Now, today's lecture is a bit of a rant because it's only in the university atmosphere that you can throw things out and hope that you hit somebody who is interested enough in something way out there, and hopefully we can take it further on. And of course, it's a huge topic, so I'm taking a couple of stones and skipping them over an ocean and trying to fit it all into 45 minutes. So please, I do apologize for it being a bit disconnected if that's how it sort of ends up. But just to give you a bit of a structure for today's talk, maybe we'll go through, why model house performance? Can we model how we live in our houses? What are the components of a building energy simulation model? Do we model for design, compliance, or performance? What's hard to model? What's harder to model? What's hardest to model? And then some of the bits that we can do well, some of the bits that we're still thinking through, and then some, I'll throw it open to you guys and we can have a discussion.
We've had some feedback from from attendees saying, please feel free to rant, PC. So you've certainly got the support.
Thank you for that. So why model thermal performance in houses? Obviously, you can model many other things. And I guess for me, it's usually if I want to understand how a building performs, if I want to make design decisions, if I want to compare against some set reference building like most standards require you to do. We're trying to model or predict energy consumption or greenhouse gas emissions, maybe look at light, maybe look at comfort. Nowadays, we're very much interested in indoor air quality, pollutant concentrations, CO2 levels. We're starting to get into mold and moisture, and possibly there are other things I've missed out as well. Okay. What exactly is energy simulation? So in 1 minute, you build a model. So you have a geometry of the model. You put in all materials of construction, windows and framing. We think about things that cause a building to become uncomfortable. So energy from the sun, heat loss or heat gain from the fabric, and whatever you do inside the building that you're living in. Air exchange, either ventilation, which you want and have designed for, and infiltration, which you don't want, and your house is leaking. You have some things about how the building is used, how you use your living rooms, your bedrooms, what do you do, And then, of course, the systems that are in that building. So lighting, air conditioning, heating, that kind of thing. Then you take that model, you make it respond to a climate file. In this case, typically we're looking at 1 hour interval data. You use a calculation engine that looks at heat transfer, mass transfer, all of those bits and pieces. There's millions of calculations going on under the hood. At the end of that, you're looking for, well, if you're interested in energy use, you're looking to predict what is the energy use by end use, by different systems. And of course, since you spend all that time and money and energy, you're then trying to optimize it by doing some what ifs. If you are not interested so much in energy, but you're interested in comfort, you might do something like this. Here is a living area. You define comfort as being able to place the air temperature and in the space between 19 and 26. You're interested in 8 a.m. to 10 p.m. because it's a daytime use building. You're looking at for the month of July in winter. There's 434 hours in that time frame, of which you predict that about half is comfortable, which means about half is uncomfortable, of course. And then to sort of put a context on house energy use, if you look at this chart, we're only dealing with the 40% for heating and cooling and possibly 7% for lighting, right? And that's when you start to look at why codes are looking at water heating and appliances and refrigerators, and why we have MEP schemes for some of these things. But the 40% and the thermal comfort is very significant. So that's why we do focus on what we're doing. So what are the things that we can sort of look at? You know, some of the things that we need to put into the model in some form of realistic, in a realistic manner, so we can actually model the heat loads and so on, are things like, when do we use systems inside the houses? When do we use lighting? What time do we cook, and how much energy do we use for cooking? What sort of appliances are in the house? When do they work? Do they work differently in summer, winter, and the middle season months? So those are kind of, we call them schedules or profiles inside a simulation model. And then you might want to think about how we live in our houses. So for example, you know, some days we're tired, it's too hot in the house, so we go and bang the AC switch and the air conditioner comes on and it does the work for you. If you are living in a leaky old house, even in Sydney, in winter it's pretty cold and we might have the heating running all the time, okay? In the so-called comfortable months, we may need to manage the house. You know, we may need to open and close windows. When was the last time we did that? Okay, so some of these things we can model, some we can't model. So we need to think about some of those issues. And then there's always the question, is our modeling accurate? What do we mean by accurate? And can we represent all this complex behavior inside a model? And the short answer is no, right? But we can test an ideal design. We can test for a minimum compliance in performance. We can test against a reference and improve against it. And, you know, one of the things that we always talk about, all modelers in all fields of study, and I think George Box, the statistician, said this many years ago, all models are wrong, but some are useful. And we want our models to be useful. We want to be able to make some design decisions based on what we're modeling. So I'm going to talk about, you know, what is hard, what is harder, what is hardest to model in this context. And I should say probably the easiest, which is still hard, is to model a box that's air conditioned using an ideal system. That's pretty reasonable. We've got most of that under control. It rapidly escalates when you try and model some real air conditioning systems. Fans, boilers, chillers, control systems, VRF systems. It gets even harder when you start to talk about modeling natural ventilation. Then you're talking about heat balance, and you're talking about airflows, which are mass balance, and you need to solve those equations in the same time step. And what we think we can do, or what we do almost naturally in some houses, it becomes really quite complex to run those calculations. And I think that the hardest is to be able to model a building which runs in what one calls a mixed mode. You sometimes close the building up and you heat or cool it. So in winter, you might close up the building and heat the building. In summer, you might close up the building and cool it. In other times, you might just switch off all conditioning systems and open the windows, let the sun in, keep the sun out. That mix is really quite difficult to do with any sort of realism. Okay, mixing mixed mode with real air conditioning systems is extremely difficult. And there's a lot of papers around, and you read them and you go, well, you know, you're looking at one thin slice of the pie, right? So what is it that we can model? What are the things that we can represent reasonably easily? What are the things that are not so easy to do? And what are the things that we're still coming to grips with? Okay. And we've had, you know, in the teaching training that we do, we use as much of this as possible. So we can do things like suns and shadows. You know, we can reliably model these things. So on this model that you've got on the page, the thing that I want you to look at is this little bit which is sitting at the back of this semi, and a number of pictures that are going to go coming forward in this presentation are looking at the performance of that bit over there. So that's south facing, and it looks out into a garden. And this is a early morning winter time shadow sun penetration type study. And the reason I'm showing it to you is these are quite reliable. Here's a post-construction picture taken as roughly the same time as the model. You can see that the predictions are pretty good. Okay. We can do daylighting. We can do simple daylighting. We can do complex daylighting. This is a very simple analysis. Static uses a uniform cloudy sky, and that new bit has got a whole lot more light than the old bit of the house. But as a design decision, I'm looking at this kitchen, and you can see that one part of the kitchen is bright, that part is dark. So the design decision was to put in a solar tube. So that changes the character of that space. I didn't need to do any numbers. I just needed to look at the pictures and make a decision. Those are things that we can do well. We can model window performance reasonably well nowadays. Here are two windows. We look at three types of performance. We look at daylight. We look at solar energy coming through the windows. So the SHGC, solar heat gain coefficient, is just the percentage of solar energy that comes through the window. 54% in this case, 55% on the glass on the right. But the light transmission is very different. 14% on this one, 63% over here. And depending on how you select that, you have a way of tuning your glazing systems. Bit more difficult to work out how the performance of the window is to heat loss and heat gain. The window has frames. Typically, the frames are metallic. Metal frames conduct heat much faster than the glass. You may have a fancy double glazed argon filled piece of glass, but if you've got a poor frame, you're going to lose a lot of that performance. So how do we work this out, you need an external program to come up with the total U value of the window system, which you then put into the simulation, and then the simulation uses those numbers. We are beginning to get to a place where we can deal with natural ventilation. Okay. Air is stupid. It never seems to follow the arrows we draw on the page. It seems to follow physics. It likes to follow physics. So here's a visualization for 1 hour. The wind direction is in the red arrowhead. We can see that better in the next slide. The blue arrows tell you how much is going in. The red arrows tell you what's going out. And this one, if you think about it, is actually quite a non-intuitive picture. The air is coming in from a high window and leaving from a low window. Okay, air is stupid. Okay. Well, the other stupid thing about air is that if you don't have a flow path for the air to move from one side of the building to the other, it actually doesn't work. For example, in most houses, we close the bedroom doors at night. There is no ventilation flow path. Your natural ventilation strategy might not work very well in those conditions. However, we have got to the point where on this very simple model, I've cut a floor plate hole for the staircase. And then if you look carefully, you'll see a black arrow, which in addition to the blue and red arrows that you can see, shows you the transfer of natural ventilation from the ground floor to the first floor and then out the windows. So those are about 96 liters per second. You add those up, that's 400, and you can see, if you look carefully, that's about a 406 liter air transfer across from the bottom to the top. So we're getting there, you know, and one of the courses that we used to run called Building Energy Analysis in University of Sydney, we used to basically give the kids a challenge to be able to pick a house that inspired them and then try and make it work using just natural ventilation, no heating and cooling, and passive solar design. Okay, it was a really exciting course. I enjoyed it. We are beginning to be able to do things like this reliably. What is the impact of an external blind in a space? So if you look at this graph, I'd like you first to notice that the bottom graph is temperatures, the top graph is solar radiation. Okay. The green line is the ambient external temperature in Sydney on the East Coast. Okay, you've got one day which is almost 35 degrees, another day which is about 30 plus. Most other days are 25, 28, 29, that sort of thing. Okay. If you look at the graph on the top, the red line is solar radiation coming in through west-facing windows. Okay. Afternoon, the sun swings over and you get this enormous amount of energy coming in through this west-facing window. And because of that, the mean radiant temperature that the resident feels is in the red line below. This is the mean radiant temperature. It's not the air temperature. Okay. And you can see that although the outside temperature is 28, 30, the inside temperatures are like a solar oven. You're getting to 40 degrees centigrade, a very uncomfortable space. So what should the design response be? Well, I should try and cut out the solar radiation somehow. The blue line shows me scheduling an external blind, cuts out all that solar radiation coming in. And the response to that is the blue line below. The mean radiant temperature drops by about 8 degrees centigrade, which is really quite significant. You would need an air conditioner in the house, okay? And that's what it is. So on this house, there are blinds, external blinds, remote controlled. They work perfectly. I'm sitting in that space, okay? Now, that's to do with summer. What about winter? Okay, here's an article that was done in the Sydney Morning Herald in July. And I've sort of cherry picked some of the statements that he's made. It'd be a great article for you to go and read. And if you look here, you know, it says that there are 2,600 Australians killed every year due to exposure to coal. That would seem really strange, okay? And if you talk to, I'm sure you've had relatives who visited you from Europe, Germany, Sweden. I had relatives from Canada, and they spent a week with me in August, and they said that was the coldest that they'd ever been. And I'm looking at them and going, really? It's minus 20 where you live. But that's because in Australia, we really haven't paid much attention to building warm houses. So one of the things that really affects the energy use and the thermal comfort inside a space is leakage, infiltration. So we've got some models here to show you. So this is a typical business as usual, typical Australian homes, measured on average about 15 air changes per hour at 50 pascals. That's just a test frame. And you can see here that in the middle of winter, you're using about 20 kilowatts of energy to cool the space to about 20 degrees centigrade, okay? Every time you cool, the warm air is leaking out through the building. You're just putting lots of energy in. If you tighten the house, you can drop the heating energy extraordinary across the year. But you've already done the other things. You've done insulation, you've done windows. This is just air leakage. Once you do insulation, you create a thermal difference, a temperature difference. Once you have a temperature difference and you have moisture in the house and from the products of construction, you have high levels of vapor in the house. You have a propensity for mold growth. If you keep your house closed, you have a propensity for carbon dioxide concentrations to increase. So the next step, if you want to avoid mold, is you need to put in some sort of a system. So here you have a mechanical ventilation system with heat recovery. So what you can see is that the blue bits are where you supply air from outside, and the red is where you exhaust air from the toilets, from the kitchen, from the bathrooms. And you take all of that air through a heat exchanger. So what you bring in is not cold air in winter, but neutral air. If you do that, you drop your energy use for heating even more. In terms of numbers, if you look at that, what you've just done is you've dropped your heating energy requirement by 3/4 approximately, and the size of your heating system by about half. And that's one bit that we still haven't really cottoned on to in Australia. We have some pretty uncomfortable houses, and I, for one, coming from where I am, don't really like it when it gets below 20 degrees. 20 degrees is my absolute limit. That's something we can do and should be doing, and hopefully the codes are sort of getting towards there. If you go forward, we can work with renewables. They are a little bit difficult, but we're getting to grips with them. We're trying to understand how they work in a manner that you can use the energy that you generate in the building before you send it out to the grid. So you need a battery. We're understanding that when you look at the generation across the year of a PV system and compare that to the energy use in the building, it's a double whammy. We use more energy in winter, even in an efficient house, and the solar system produces the least amount of energy in winter. So there is a bit of a dichotomy there which you need to work through. Okay. We've come to the point where we can reasonably well predict what can be a net zero house across the year, so that you have to still buy some from the grid, but across the year you're generating more than you're buying. More difficult is the heat transfer from the ground. Now it's a difficult problem because what happens under the ground is very slow, and we're trying to put a model which is trying to push one-dimensional heat transfer onto what is a slow three-dimensional heat transfer problem. That's always rough, okay? And to top it off, if you put insulation either as a perimeter insulation or along the edge of the slab here, you're changing the heat flow field quite radically, but it's a slow change, and the models are not really quite good at that. Okay, just having a building sitting on the ground changes the flow, the heat flow field around it. Heating and cooling the building changes the heat flow field around it as well, but it's a lagging field. It takes 2-3 months to catch up with the ground. And we're trying to do a simulation every hour and trying to work out what's going on within the building. That part is always a bit crazy. We are getting models now that are doing these things, but to try to do them in the same time frame has been for many years difficult. It's only in the last 2-3 years we've got some models that do that quite effectively. Another difficult thing to think about is bridges, thermal bridges in construction. Okay, we're reasonably good at windows. We can model them outside the simulation and can take account of that. We're getting better at looking at wall construction, roof construction, ceiling construction. But in Australia, we haven't really engaged with things like concrete balconies, okay, slab edges. And possibly they're probably not as difficult to manage as in European countries where it's -30 outside, but they still play a role and we need to think about them. They play a role not only in the thermal bridging, but also in moisture and mold and those kinds of issues. When you have cold spots, then that's a propensity for mold to come along. The National Construction Code now explicitly refers to thermal bridging. There are some competing international standards for calculations, different. Windows are modeled using one set of standards, and constructions, thermal construction in walls, etc., have used other standards, and so it's a bit of a mishmash right now. Simulation tools that we use can't do them internally. We need to do those things outside, bring them into the model, and it's something to think about. We're still working our way through some of those things. We really are still getting to grips with issues for mold and moisture. There are only about 2 international pieces of software that can do a dynamic calculation of these kind of effects. Mold is insidious. Insurance doesn't always pay out for mold because it's not an instance. It happens over time. You don't know that it's there till about 3 years after you've lived in a place. You find out about it because people who are susceptible to that start getting sick. Okay. But these are things that need to be taught at the design stage. They're things that you can't see. And it's a choice between, do we buy a granite kitchen or do we spend the money to do the detail, wrap the building, work out thermal bridging, look at linear thermal bridges, okay, look at how it affects across the year. Do we have vapor permeable membranes? They need to be waterproof, but vapor permeable. And what is even more difficult is that we live in climates that are moderate. We have a defined winter and we have a defined summer and we have a defined in-between season. A lot of the mold standards come from colder countries. They have a clearly defined warm side and a clearly defined cold side. Ours switch around across the year. It's a bit strange. We need to work out ways to work on that. We need to learn from what's already gone before and work from there. So these are areas, and I'm sure there are others that I haven't covered, and I apologize for that, where we're still struggling, to work these out, put it into an energy simulation, pull out an answer that is useful for codes, for design, for improving performance. How do they impact on thermal comfort? How does it impact on draft? How does it impact on the mean radiant temperature, operative temperature? Those kinds of issues. You have Professor Richard Didier, who I can see is logged into the meeting. He's the guru of thermal comfort. Some of these issues I'm sure he's also thinking about. And there's a lot of work to be done in these things. So with that, I just want to share a few final thoughts, and then I think we can put it out to Q&A and have some question and answers on this. Pulling all these bits of information together in an integrated model to answer even simple questions reliably can be time consuming and painstaking. The way we do it in Australia for code compliance, we use a package called Natters, which is kind of locked down. You can't really fiddle with many of these inputs. You can do some. You can do windows, you can do basic wall construction. It has an inbuilt way of doing natural ventilation. It has an inbuilt way of working out ground heat transfer. You can't change that. you can't really change infiltration, which is a really big do for heating. So some things to think about. Of course, if you put in the wrong inputs, then what you get out is not really useful. And modelers for years have been talking about garbage in equals garbage out. It's got a nice ring in the Irish words, but I won't say them, right? And then who wants to pay for this analysis anyway? You know, if you want to do all this for a home, if I gave my fee to somebody, he will tell me to go to the proverbial. So there's something to think about there. Can we resolve some of these things into simpler models? And the difficulty is that if you don't do them in an integrated fashion, then it's very difficult to look at an integrated output. We do have building codes, and their role is to ensure that minimum performance standards are met. That's their role. And we have other voluntary systems like Green Star in Australia, which are pushing the boundaries, you know, going beyond the code. So there are some drivers to sort of improve, predict performance, and we're all learning. So hopefully this has been useful, and hopefully we've got some questions that we can start talking about. And please feel free to rant at me. Over to you, Daniel.
Thanks so much, PC. That was a really informative and well-paced talk. So as PC mentioned there, it's time for Q&A. So please feel free to pop some questions in if you haven't done so already. We probably have about 10 minutes or so to go through things. I know that there have been a few have come through firstly in the chat, so I might just go through those. So thank you to Mahalath and David for your questions as you went through. So Mahalath asks, who decides what's comfortable besides varying by climate, varies by person as well?
Yes, you're very right, Mahalath. If you look at one of the measures that's used for monitoring comfort or predicting comfort in air-conditioned spaces, called the predicted mean vote. What is called thermally neutral assumes that 5% of the people don't feel comfortable in this thermally neutral space. We're all different. And yes, I think, as I said, when I used to take my kids back to South India for holidays, and it was so-called winter there, and it was 25 degrees, and my kids were in shorts and t-shirts, and other people were wearing woolen sweaters, and they looked at each other, and each one thought the other was mad. So, it's, I think that's a very valid question.
And David, I think his more comment just says, if I recall correctly, it's handy to think of it like this: a square meter of solar exposed standard glazing in summer takes on the equivalent of a kilowatt of heat in 1 hour. Thus, to maintain comfort under those conditions, one might need a kilowatt of electrical cooling capacity per hour for that one window. To offset that heat gain, these figures are rough. PC, feel free to correct, but when planning for energy efficiency, it still helps to think about the mechanical energy one has to use to offset the passive solar gain if one ignores good logical passive design that provides shade in warmer months.
Thanks, David. You're right. It's the number that you've given is a good measure, but only when the sun is shining brightly and it's kind of perpendicular to the window. And that hardly ever happens. So it's a very dynamic thing, and depending on which location you are at, those numbers change quite strongly. One of the things we found out was that, even within Australia, for example, in Melbourne and in Hobart, the solar radiation is much lower than, say, Sydney or Adelaide or Canberra. And if you end up having to design quite differently in those locations.
And then Noy has asked, he just mentioned, well, thanks for sharing. What software are you using for natural ventilation modeling?
Oh, okay. The engine is Energy Plus. We're using the Design Builder graphic user interface, and those pictures that I showed you are from Design Builder.
And Malay has says thanks again. How are 2 layers of glazing modeled in these tools? Say glass wall window letting sun into a corridor with an internal glass wall window to a bedroom.
Yeah, those models they're doable. You need to sort of work through some of the settings, but in theory, those models are pretty easy. Well, I won't say pretty easy, are doable. We've done runs within we had a Professor Jan Hensen come here from from Eindhoven, and he was here for a semester, and we ran with the students a model where we had exactly that sort of a model, and we looked at how the ventilation sort of worked within that corridor and then back into the room if required. So it takes a little bit of setting up, and that's why I said that pulling this information together, even in sort of what seems to be a really simple question, can be quite complex, but it's doable.
Thanks. Ronald is wondering, thermal heat sinks in buildings, use of floor slabs and walls to absorb radiant energy in daytime and release over nighttime. Good in winter, not so good in summer. Any thoughts?
Absolutely. That's when your operable external blind comes into its own. You allow the sun to soak into your slab in winter days, and you position it so that it can, and you make sure that in summer it doesn't do that. I mean, thermal mass is like a battery. You need to charge it. If you can't charge it the right time, it's pretty useless, because then it sort of charges at the wrong time and discharges when you don't need it. And I think anyone who's lived in a concrete apartment which is facing south will be able to kind of understand that it's really cold over winter because the slab is just really cold. If you've got an apartment that faces west and you've got a lot of glass and you don't have an external blind, it's the reverse. It really charges up in summer, and then the whole apartment is hot, and it's a really uncomfortable space to be in. So you can do that, you can model it, but again, it's not a straightforward model. There's a number of settings you need to tweak, but you can get those outcomes in there. And I can see Richard's question, and thank you, Richard, for that question. That's a wonderful question, something that I missed completely. Behavior is extremely important. And in all the models that we're doing for single houses, we're really guesstimating on a behavior schedule. We're deciding when people are switching on lights, and when they are switching on equipment, and when they're cooking. Those little graphs I showed you right in the beginning, this one here. And of course, we're making assumptions like everybody does exactly the same thing every day of the week in exactly the same time. Those are assumptions that are in there in the model, and obviously those are some of the weak points of the model. There has been some research done. I'm sure you're aware of some of that. Anything that we can do to improve our predictions with modeling a reasonably better profile for any of these behaviors would be wonderful, but we need to go with what we have. With commercial offices, it's a little bit easier because you roughly know that about 80% of the population will be there between 9 to 5, so you can kind of assume that that's okay. But in residences, it's absolutely impossible to do that. You can have two identical houses, have completely two different energy profiles because of the way people live. You might have one house where everyone goes off to school and work during the day, and another one where you have somebody living at home during the day, and the exact same house would have a completely different performance. So in that sense, it's been impossible to generate a performance type rating system for houses. It has been much easier to do that in offices where things are more reliably predictable, or schools where things are more reliably predictable. But that's
no lockdown schedules at all being developed this year or anything like that.
post-COVID.
Work from home schedules, etc.
Yeah, I know of some people who are doing measurements. Lena Thomas from UTS is measuring 40 houses in the Fairwater project. Maybe you can ask her questions when she starts to put some numbers out. So there will be a pre-COVID and a post-COVID thing.
Great. Okay, I can see two more questions here. I noticed that also David has put a significant comment in the chat box, but we might just go to the two Q&A ones first. And if there's time, we get to David's, and I'd say that will probably bring us close to 2 o'clock. So Malay just has, you modeled phase change, bio-PC type materials. Are there significant opportunities in using them?
Okay, very good question. We do have models for phase change materials within the Energy Plus engine. In fact, I believe that some of the bio-PCM materials are already programmed into the design builder interface, but using them is not straightforward, and I must confess that I haven't had much experience with them. If you contact me, I can put you in touch with someone in the US who was willing to give me a demonstration of how to do that. So that offer is there for you.
And Noy was just wondering whether you or Team Catalyst has ever worked on a Green Star performance project, just asking because this can involve on-site measurements and occupant surveys.
Yes, we have, and yes, we're aware of that. Yeah, I believe that anything where you can, validate your model using on-site measurements and occupant surveys is a great thing. So it's the one thing that building owners don't like, because the messaging is not controlled. An occupant says what he feels, not what the brand requires him to say. So yes, I'm all for it. And we have worked on some projects like that.
David said no need to respond, but he just did note that there hasn't really been much of a large scale study into HVAC energy end use. And this is sort of looking at apartments. So I think that comment's probably worth having a look at if people have time, and certainly points out to some further research needed.
Yeah, I think the short answer to that is the way we model is, particularly for code compliance, is not the way we use air conditioning in homes. We model either for code compliance at this point, we model that most of the house is either heated or cool. And typically in many of our cities, we don't do that. We air condition a living room or we heat a bedroom. We do that intermittently, but it's still a good way of comparing design A against design B. And I think it comes back to Richard's question on behavior. If we had a better model of behavior, which we could program into our models, it certainly make for a more robust sort of outcome. I'll leave it at that.
Thanks so much, PC. So firstly, thanks to everyone for coming along today. There's some great questions there, and thank you all for your participation. And also keep an eye out for emails for more online events that'll be happening in the future. But particularly thanks, PC, for a really clear and well-structured presentation. I thought you pitched it really well for the different kind of levels that people are at. And a very kind of diplomatic rant, if ever there was one. But thanks again for being part of our season 2 ADP speaker series. So stay safe, everyone, and we'll see you next time. Thank you so much.
Thanks for the opportunity, Daniel.